Hi everyone, I hope you're doing well. This is lesson 4, which is all about Venn diagrams and kind of organizing outcomes based on Venn diagrams. And it's one of the ways that a tool you can kind of use to figure things out for probability. And so a Venn diagram really is just a box generally, and that box represents the universal set. And the universal set, which we've talked a little bit about, is like all possible outcomes in a given scenario. So like if I said I'm going to roll one die and there's 6 sides on the die, the universal set would contain all of those 6 outcomes. And within this box, sometimes you have multiple sets, so multiple circles. If you're not, might have one circle, and you might have a specific type of outcome, and those are represented by the circles. So for example, this Venn diagram shows set A, so we've got an A just outside of the circle within this universal set, which gives U here besides the box. Everything that is not A is represented outside of the circle A, and it's given this A prime. This is A naught, pronounced A naught, which is the complement. So everything that A isn't, and it's the shaded region here. So everything that A isn't. So like if I said, A, let's say A are all of the even numbers on a single die. You could represent the numbers in here. So even numbers, that'd be 2, 4, and 6. And all of the odd numbers, not 3, 1, 3, and 5 would be out here. So those would be the individual outcomes of that. Sometimes we want to talk about the number of outcomes, and we'll get to that. But like basically, if I was to say, okay, what's the number of even? So the number of even or number of set A, well, there are 3, so that's the number. So the n represents the number of whatever the set is that we're talking of. So let's say we had this situation where the sets U, which is represented by these numbers, A, and A prime would be these. And so we can draw a Venn diagram to represent this. So let's say we got A, draw a circle. Here's U, my universal set. And everything else would be A prime. So I would put my 2, I guess a 7 and an 8, because those are the things included with my set A. And the 3 and the 5 would go out here. And everything within those two things is formed with the universal set. Pretty straightforward. So again, if I wanted to talk about the number of these items, I would put number or n of U, which is equal to, in this case, 5 different numbers. What's interesting about this is that the number of A plus the number of everything that isn't A will always equal the number of the universal set, which sometimes is called S, but let's go with the IB way, which is U. And so that will always be the case. And in probability, that transfers into the probability of A, which we've talked about, plus the probability of A naught is always the probability of everything. And the probability of everything is always just going to be equal to 1 because it's 100% of all your outcomes. So we use that formula a fair bit. So there's a bunch of notation within Venn diagrams, and sometimes the notation is the tricky part. For example, if I wanted to talk about a subset is something that is contained within another set. So for example, if B is a subset of A, so this represents subset. So this kind of sideways U with an equal sign or a line below it. Then every element of B is also in A. You're not going to get a lot of that notation, but you may, so I'm including it here. So this shaded B, the circle representing B is placed within the circle A here. And so every element of B is also an A, and there's our notation. Probably more important is this idea of the intersection. And the intersection between two overlapping sets here, again represented by the highlighted yellow, it has a notation. This would be A intersect B. And it's kind of an upside down U, kind of looks like a big N maybe, or a horseshoe. This is really all of the things that are in A and B. And then it has a lot of important context. It's the and part that you really have to remember. So A intersect B consists of all the elements common to both A and B. So it's a shaded region here in the middle. The union, which is really, if I wanted to talk about anything that is contained within either of the sets A or B or both, then you get this, A union B, which is a U for union. So intersection, upside down U, union, just straight up U. These are all the elements that are in A or B or both. And so shaded would be everything, the overlap and so on. So this union is really A, we say, or B, A or B, which is the equivalent of A union B. So one of A or B or both. And a couple things we've talked about, mutually exclusive or disjoint sets. So that's where you have no common elements. If I wanted to talk about the union between these guys, I would have the union of A and B. Then you would just fill in both. Note that the intersection really is 0 or the null set. So it's just an empty set. This is called the null set. It looks like a 0 with a line through it. It's also called the empty set. So things that have no common elements would be this mutually exclusive or disjoint. So let's just, do a little practice with this. So the example here, suppose we've got sets U, A, B, and C and D. Illustrate each of the following with the Venn diagram. So it says A intersect B. So we go to A, look at A, and we look at B. Looks like A are the odd values of 1, 3, and 5, and B are even numbers. So in this case, they have nothing in common. So A intersect B would be the null set. So it looks like that. Not shading in anything because there really isn't anything to shade in. A intersects C, take a look at these ones. So we got A already. C does have some common elements. So I've got A, and the size doesn't really matter. It doesn't have to be proportionate to the size of the set. There's A, and there's C. So things for A that are just an A and not C would go here. So I guess that's just the 1. And this would be the 3 and the 5 because it's also within set C. And then what's left over would be the 2 and the 6 out here. Everything outside, we could continue to fill all those rest in, but we'll just leave it for now. Often when we're talking about probability or dealing with anything to do with probability, we really want to know the number of this. So if I wanted the number of the A intersects C, then I would say, okay, well, there are 2 items here that fill into the middle. So that's this area. Then the last one, C intersect D, you can kind of try this. This would be, look at them, C and D. So D is actually within C because it would be a subset, and there's the numbers. The number of C intersect D would be equal to 2. And if I was to draw this, because D has all of D's elements are within C, I just draw it inside. So there's D, here's C, 3 and 5, and then what's left over for C, I guess, would be 2 and 6. So the intersection is actually the subset. So sometimes that pops up. So we can use this, and there's lots of different things you can do, and it does get fairly complex in terms of the notation. Fortunately, we don't have to get too deep into that. But it says we can use shading to show various regions or sets on the Venn diagram. For example, 2 intersecting sets A and B, like this. In this case, we'd say obviously this is just A is shaded. This would be A intersect B. Hopefully that makes sense. This one's a bit trickier. Notice everything is shaded except for B. So we would say, really, it's everything not B is shaded, or B prime. That can be useful when we're talking about everything that isn't something. So it says shade the following regions for two intersecting sets, A and B. So they're saying that they're intersecting. So A and B. If we shade these in, we'll label them here. So shade them all in. There's A, there's B. We can also put U out here, but it's not always necessary. This one, everything that's intersecting between A and B. So we know they're intersecting. So everything that A isn't intersect B. So everything that A isn't, if you look at this one again, this is everything that B isn't shaded in purple. Everything that A isn't would be everything shaded, but it's also the intersection with B. So this intersection with B. So really everything that's not A is outside of A. What intersects with B outside of A would be just this. And so this is that A prime intersection with B. So that one's definitely trickier. And then the last one here, A intersect B, so let's draw it, prime. So if you imagine this, everything that is not the intersection between A and B, everything that is not, and that's because of this prime, the intersection of A and B. So A, B, and we know the intersection. I'll do it in red. This is the intersection. So everything that is not the intersection, we're going to shade in. So that means everything except for that red part. So again, this is A intersect B. So kind of going quick, so if you need to catch up, just pause the video at any time. This is just kind of some of the background stuff that you may encounter, but it's not necessarily the focus. What we want to do is use this stuff in order to solve problems, and that's what we're going to get to below. So here it says Venn diagrams can be used to solve probability problems and to establish a number of probability laws that we'll talk about. Let's take this example. It says in a class of 30 students, it says 19 study physics, 17 study chem, and 15 study both these subjects. Display this information on a Venn diagram, and then determine the probability that a randomly selected class member studies the following. So let's start by creating the Venn diagram. So let's do a little box. There we go. And within it, I've got two sets, the physics and the chem, and you can see 15 study both. So we know there's going to be an intersection like this, and we'll just label these. So let's say this is physics and this is chem. When you draw these and you want to fill them in, we're really just concerned with the number of students. We don't care about their names or anything else, so we're just going to fill them in based on that. So when we draw this, we always need to start with the middle intersection. And then we're going to make our way out. So the middle are the 15. So we know that the intersection, there are 15 people. If we go to chemistry, let's focus on it for a second. There are 17 total that study chemistry. That means, I'm going to shade this and I'll delete it in a second, but this whole thing is 17. That whole shaded part is 17. If I already have 15 within the middle, that means I've got 17 minus 15 remaining to go in this, which would give me the 2. And so that's the total number who are just studying chemistry. And then the physics, we'll do the similar thing. We've got 19 who study physics, so 19 minus 15. And so the total who are just physics would be 4. And we could easily figure out the total number of people then who don't study either of these subjects, which we need to do. And that's the part that's going to fit on the outside. So within the square, or the rectangle rather, but not into the two sets. And we can figure this out by just taking the numbers within these sets. So I've got 4 plus 15 plus 2. That's the total number of people who study either physics or chem or both. So I add those up, I get 21. Therefore, the total number of students, which was 30, minus 21 gives me the number of people who don't study either of those subjects. So I get 9. So that 9 is represented outside like this. So the Venn diagram is useful because now we can kind of figure some things out based on this. So let's start with what's the probability that a randomly selected class member, so let's go with A, studies both subjects. So the probability of both. So really we're saying the probability that they do both. So I get physics and chem. So I take my number, which is 15, over the total number of students in the class, 30, so I get 15 out of 30, or 1/2. Pretty straightforward. So we really didn't need the Venn diagram for that, but it will be helpful for some of the other ones. Second one says, what's the probability they study at least one of the subjects? So probability at least one. So in this, what we're figuring out is that they could study one or two so either subject. So really it's P union C. And that's really all of these things, 4 plus 15 plus 2, which we figured out of 30, which gives me 21 out of 30, which is the same as 7 out of 10. If we go to C, just make some space here. And you can try these maybe now that you got the hang of it. They do get a bit harder, but so physics, let me just use the P. And you can write physics not C. You don't necessarily need to worry about the notation. So the number of people who study physics but not chem, so really I'm just talking about this 4 people. So physics not chem. And so I've got 4 out of my 30, and that simplifies into 2 over 15. Part D, the probability that exactly one of the subjects, so probability of exactly one, so that could be they study just physics or just chem. So I'm only looking at those 2 numbers. So I've got 4 plus 2 over 30, which simplifies into 6 out of 30, which is 1/5. And then the last one, neither subjects. So that's the part we already figured out kind of at the beginning, the number who don't study either. So probability of neither is going to be 9 out of 30, which becomes 3 over 10. And that's it. So something you can use hopefully as a helping hand in order to solve some of these problems. So within this is this idea of what's called the addition law. So it says if A and B are 2 events in a probability experiment, then the probability that either one of the events will occur is given by the addition law. And it's pretty straightforward. It really is the probability of A or B, so this is the or part, the union, is equal to each probability, so probability A plus probability B, but sometimes you get this overlap, so we have to subtract the A intersect B. And the reason is because we double count those numbers, and we'll have some examples here in a second. So this is the and part, which is the intersection. So let's say we have some abstract situation. There's no, A represents this or B represents that, and it just says if the probability of A is 0.6, probability of A union B is 0.7, and the intersection is 0.3, find the probability of B. So we could just take this, and this is a formula that you are given on the IB exam. I'd take each of them, set up the formula, and just sub in and rearrange. So if I want to find probability B, we'll take the union, it's 0.7 over here, A is 0.6, don't know probability B, but I know the intersection here is 0.3. So we just rearrange it. So this would be 0.3 on the right side. I'm going to move that over, so I get 0.7 minus 0.3 equals probability of B. So the probability of B is just 0.4. So a situation where you really need to know that formula, or at least be able to use it, because it is given to you. So this idea of in this case, we had intersection versus what can be called mutually exclusive or disjoint sets. If two sets are mutually exclusive, that's a fancy way of just saying they're separated or disjoint, then the probability of the intersection is 0. So the addition law is actually even simpler. If I just take probability of A union B, I've got the probability of A and the probability of B with nothing to subtract because there's no double counting. So I've just got the probability of each added together, which lots of situations have, no overlap within them. So all of these things, and it's just reiterated the same thing below here, but let's just take an example of this. So it says, find the probability that when you toss 2 standard dice, that you get a sum of 6 or a sum of 8. So let's say the event A is the sum of 6, and event B is the sum of 8. If I want to find the probability, I have to first think to myself, are these things mutually exclusive? And meaning, is there no overlap? And yes, there's no overlap, so I would say yes, they're mutually exclusive. So that means I don't have to think about subtracting something. So if I say the probability of sum of 6 or 8, then it's really just going to be the probability of each added together. And I've got the little table we created from before, so just in case you've forgotten, here's my sum of 6 right there, and here's my sum of 8. If you count out each of those numbers, there is 5 possible outcomes for a sum of 6 out of 36, and similar with 8, we get 5 out of 36. And we're just going to simply add those together. There are no overlap between those two. So we end up with just 10 out of 36, which you can simplify into 5 out of 18, like that. Pretty straightforward. But let's say we get to the next question. It says, find the probability that when you toss 2 standard dice that you get doubles or a sum of 8. Doubles really just means the same number on each die. So for example, you could have a 1 and a 1 or 2 and 2 and so on. So again, we'll just set this up. So let's say event A is doubles, event B is sum of 8. Are these mutually exclusive? No, they have overlap. So the intersection, and we can look at the little table if we want. If you look at the intersection of doubles, so 1 and 1, that's that 2. A 2 and 2, that's that 4. A 3 and 3, that's that 6. And it kind of goes like that, just like this. And then, sum of 8, I didn't put that. Then I've got this sum of 8. I've got this one, and then there's the overlap. There is one intersection point where you've got intersection with 2 4s. So one outcome is the intersection. So when I set this up, the probability of A union B equals probability of A plus the probability of B minus the probability of the intersection. So doubles, there's 6 of them, so I've got 6 out of 36. Sum of 8, I've got 5 out of 36. And then the overlap, I've just got 1. So put them together, we actually get the same answer, just by coincidence, as the one above, 5 out of 18. So you have to kind of critically think, is there going to be overlap between these things? And that sometimes is obvious and sometimes not obvious and a bit more challenging to figure out. Okay, the next one here, this is when you get 3 sets, hence why we see these 3 circles here. And I'm just going to include around it, really, we should have a box. So let's add that in. Oops, that's way too big. Don't know if I can select it. Let me just do it over. Let's see here. There we go. Okay, so in these scenarios, you've got 3 separate sets. And if we read through it, it says there are 140 grade 12 students. 52 signed up for bio, 71 for chem, and 40 for physics. The science students include 15 who are taking both bio and chem, 8 who are taking chem and physics, and 11 taking bio and physics. Those are all the intersections. And 2 people are taking all 3. What's the probability that a grade 12 student is taking no science courses? So represent this using a Venn diagram. So when we create these, just like before, we really have to start. Oh, I'm going to have to restart this. Go back. Can do it. There we go. We have to start in the middle. In the middle this time is the triple intersection. So I'm going to start here. There are 2 people taking all 3. And we should label these. Let's say this is bio, this is chem, and this is physics. The key when I create this is that as I move out, I'm going to subtract what I've already put into the bubbles. So we start with that one. There's my 2. That's easy. And then we say there are 11 taking bio and physics. So I go to bio and physics, and I'm just going to highlight there are 11 in this whole overlap. So that whole piece, because that's the overlap between bio and physics, has 11. So I've already got 2 put into the middle. So that means this, what's left over, I take 11 minus 2, and this one's going to be 9, if that makes sense. So I've got 9 plus 2 is the total, taking both. And I continue like that. I'll just do one more to show you. There are 8 taking chem and physics. So go to this section. So this whole thing is 8. Again, I've already got 2 in the middle, so easy math. This is just 6. And then the next one, hopefully you can get this, 15 taking both bio and chem. So that makes this 13. So 13 plus 2. I'm just going to make this a bit bigger and brighter there. And then as I fill out the outer parts of each circle, let's go to the bio one. 52 have signed up for bio. Right now I've already got 9 plus 2 plus 13. So what's that? That's 24. So I've already got 24 in the bubble. What I need to do is say, okay, well, what's left over to go in the outside of the bubble, out of the 52? So I take 52 minus 13, minus 9, and minus 2, which gives me 28 who are taking bio only. So those are the students who just are studying bio. And I can do the same thing for all the other ones. So the chem, total number is 71 minus the overlaps. And so these are the people just taking chem, which there's 50. And you can try out the physics one. That's 23. So we've got our Venn diagram. There's a lot of information contained in here that you could use to answer questions. So in this case, we did, I think originally they were saying, what's the probability that a grade 12 student is taking no science courses? These numbers represent all of the people taking at least one science course. They could be taking 2, they could be taking 3, and any mix of them. So the number of no science is simply going to be the total number of students, 140, minus all of these numbers added together. So I got 28 plus 13 plus 2 plus 9 plus 6 plus the 23 plus the 50. And notice I only wrote those numbers once because that's just the number. I don't need to double count. I've subtracted all the ones where it's double counted. And so I get 140 minus 131, which gives me 9. I'm going to put that into my Venn diagram. There's a 9 outside of here. And so in the end, the probability of no science, student taking no science, is going to be 9 out of 140, which I don't think you can reduce that fraction. So these 3 set Venn diagrams, it may come up on an IB exam. It has come up in the past few years. So good to be able to do, and they're not super difficult. So good to practice and try them out. Okay, here's your practice questions. Here, I thought this might be interesting to some of you. The intersections of Greek, Latin, and Russian alphabet. So you could probably answer to me which one's which. Pretty sure this one's Greek over here. Yeah, anyway, we can talk about that if you want to in class. Try these questions out, and if you have any problems, just let me know. Okay, see ya.